For lunch is Rolf Ent, who's going to talk about JLab 12 GeV science and outlook for electron collider.
Yeah, so originally I looked at the program a little bit, and I was supposed to ask about JLab 12 GeV science, but okay, that's fine. But I decided I'm just going to make a Craback talk. Unfortunately, it got made only yesterday evening, this morning. But I'll talk a little bit about 12 GeV science and what more is the impact is to EIC, and speculate a bit how the science is connected, what new science. I also fold in a little bit what I think some pieces of new science has come up in the last few years, which I didn't directly see in the program. So I'll just talk a little bit about those things. So I fold a few things in there, like hopefully to helpful towards if we talk about a revision of the white paper, what are we going to do? And there's more than that, isn't it, than what I'm talking about. It's just, I just looked at things which I thought were missing. So I'll talk a little bit about recent highlights, the ongoing program, the near-term 12 GeV schedule. I'm not going to give you the whole science you want to do with 12 GeV. I'll just give you examples of some science of relevance for EIC, give you a little bit idea of the breadth of the program. And then the last one, certainly I want to talk a little bit about emerging science for the new EIC white paper, between quotes. Talk about pioneering construction, the emergence of mass. You're going to hear more talks about mass and mass budgeted proton more tomorrow, I believe. And I'll talk a little bit about quarks and gluons in polarized few and many body nuclei. So I just do whatever I want. That's my talk. That's what I'm telling you. So JLab actually, sometimes I would say when it rains, it pours. And this is, I can show you here what came out of Jefferson Lab experiment and theory. We had like 4 Nature articles in a row, also one in Nature Communications. The rest of our colleagues in nuclear physics also had quite a few. This is all a good sign. I think that Nature starts paying more attention to us. But we had quite a bit. The big charts of the proton, pressure distribution in the proton, ultra-fast nucleons. So it went all the way from fundamental symmetries through nucleons, through 3D imaging to heavier nuclei. So quite a bit of science came out. Now this slide I just have in there to tell you, look, we did complete our CBEF 12 GeV upgrade September 2017. That's great. We happily have been commissioning holes A and holes D since 2014. So at some level the science program started in 2015. And in 2017 we had the commission runs for holes C and B. CBEF is unique. Electron beams around the world, there's not many around it. We are the one of a kind in the energy range, in the intensity range, in the beam quality range. It's pretty impressive. You see what you can do with this pencil beam-like electron beam while you control the list reversal, how much you can control your systematics. And I'll come back to that a little bit later too. So this is one famous plot. We always worry somewhere after we started the 12 GeV upgrade. Originally the idea was we would run 3 holes and then one would rate way through. And then somewhere there was some bright accelerator scientists who came with an idea, how can we run 4 holes together? Well, they came on the outside of the project because the project was already in motion. And here we are, there start different holes coming up. So since about January this year, we have been running 4-hole simultaneous physics operations. Now that sounds like you are used to colliders where there's more than one experiment running. For Jefferson Lab, essentially this means 4 independent beams. Yeah? So this is a tour de force to get 4 beam holes running. The scale, the currents can go from a nanoamp to say 100 microamp. The energies can be different. Polarization can be different. This 900 kilowatt CW beam power is close to the maximum we're allowed to have. 1 megawatt is very cut off. That has to do with all kind of site environmental constraints. That's in one area to look for holes. I mean, in the end, when we talk about EIC, we use the same, what Bernd just showed, 10 megawatt for the full site. It's the same number. And we can argue, to come back to Marcus' question, maybe we can reach 15 megawatt or 20, but you get 50% the factor of 2. In the end, you need cooling. And so there is a 12 GeV science area in all 4 holes. Hole A is in physics operation, hole B is in physics operation, hole C, and hole D. Of course, hole D already has had its first publication. They are shortly submitting their next one. We're busy there with the 2x run. That should continue in 2018. I'll come back to that later. And hole A already has publications also. It says will be this year. One is actually already there. It's on the next slide. This is outdated. And I'll come back a little bit what we're doing in the separate holes. Hole B proton radius, actually next week in the Hawaii meeting, they'll show preliminary results. Heavy photon search is being more submitted for publication, so things are coming out. I have one slide each for tell you a little bit what the holes have been doing in 2018, and this is in hole A. It's the first use of a tritium target, hydrogen-free, we call it. Tritium is a better word, hydrogen-free target at an electron scatter facility since 3 decades. It's amazing, but we have completed essentially 2, almost 3 experiments with that. This is online. This is just the ratio more or less of the proton momentum distribution, helium-3 and tritium. Depending more or less whether you believe things are more or less sensitive to a tensor force or not, this number can be 1.4 or 2. So that's what I'm looking into. But this is online. So don't look at it too much. It's just what I got online. So we get good quality data online. Well, I already had this first publication. That is actually with the titanium cross-section. That has to do with, we had an experiment measuring both titanium, which was kind of a spin-off, and argon in collaboration more or less with the consumer community, who starts building all kinds of liquid argon detectors, so they need to know what argon spectrum function is. So we measure for them the argon spectrum function. So that publication is coming out shortly too. So that's all. They're running happily in tritium, and we're supposed to finish these tritium experiments end of this year. Hole B, they actually started running. This data is, I believe, based on only maybe 1% of the data or a few percent of the data accumulated to now. I'll just show you that essentially this is their kinematic phase space. They start looking at the raw beam spin asymmetry for deep quantum scattering. And okay, doesn't look too bad. And again, this is only about 1% of the data they have accumulated now. This is also interesting. This is kind of beam spin asymmetry, so related more or less to the TMD program. But look at this. This is like 2% asymmetries, and you can look at the error bars. So the people are really moving, and I'm sure that next year there will be plenty of results coming out. So people, there's a whole session, I think, at the DNP meeting to talk about preliminary results from home. So it's not there yet, but it's clearly in motion. And if you want to know more, I'm sure that Harouk can talk for hours about this. His baby. Hole C, they have actually started with a set of calibration experiments, we call them. We just pick pieces of certain experiments we needed to anyway to understand the apparatus. As one example, more as what you see here is we did E'P. This at Tuskers 40.3. If you go back, this is in a region where the old Brookhaven proton 2P experiment saw a rise in transparency. So the question is, do you see it in E'P, yes or no? If it's there, then it likely has to do with crossing the charm threshold. If not, then there's something wrong. And so there's concretely some things you directly get out. What we're doing at the moment, we actually have started the first series of experiments relevant for the 3D imaging, which has to do with the validation, more or less of the semi-inclusive deep molecular scattering, and kaon electron production scaling meshing. That's the first motional transfer separation. So that's underway. And this is again online to show you that simulations and data are not too bad. The fact that it's different here is normally a resolution effect. Those are always difficult to simulate. But absolutely, this is all online and it works pretty well. Hole D, CLUX phase 1 is near complete. They probably are finishing it somewhere here in the Q2 of this year to get all their data. They were at 80% in May. They've analyzed 25% of the data and they're catching up now. That just has to do with when you start more or less populating the full farm, more or less using all the supercomputers. So this number is going to ramp up like crazy now because they started 2-3 weeks ago. You can see more of the spin transfer coefficient. That's one that tells you more about the reaction mechanism. This is more JLab prediction at threshold. I believe this is still the last plot they're showing. Because I heard that Senadine was worried about some other things, but this is the last I've seen. So anyway, these people are in motion too. They're ready now to getting rid of the next phase, which is like a small experiment looking at primitive scattering, looking at atom mason, atom prime transition mason form factors, and then go to what's called CLUX2. That means going to a higher intensity and also putting a Dirk-based shrink or kaon identification. So that won't start probably until fall of next year. They first will essentially complete CLUX phase 1. We'll do this test and they'll test the Dirk-based shrink. So they're moving. So the other thing is more or less that, again, some experiments is a bit cheating. We just started in 2015, but we have completed now 10 experiments. So it does look, and you see all the holes slowly being populating. Hole A is just a small number because it's one such giant experiment we started with. But 10 experiments have been completed. That does not include the full run yet, and we are happily keep on running at the moment. For the rest, it's 4.6. Hole A started, of course, earlier. Hole B and C were running a lot of experiments in the beginning to start. Hole B counts also like proton radius, heavy photon search, yada yada. Some future projects. Muller is a precision standard model test. There was a science review in September 2014, long time back. Very strong endorsements. We got CD0 approved December 2016, but the project has remained since then paused due to the budget. I think there might be some glimmering, some hope of green light to proceed with this soon, especially given that the budget structure, the budgets for nuclear physics are not looking too bad. So what we're doing at the moment, we're just assuming that will happen and setting a project structure in place. You can't really put it in place, but you can prepare for it. You're not allowed to do certain things. So that would give a full exploitation of 12 CB upgrade. Why is that? Because it will combine large acceptance and high luminosity and all kind of polarized targets. They have a piece of standard model test, a piece of nuclear imaging, a piece more of JLab production. They completed a pre-conceptual design report, the brief laws of nuclear physics. Very positive meeting a few months back, and we're gearing up now and hopefully soon can get more or less the green light from our colleagues in nuclear physics to get them a science review. Now I won't bore you too much with this, but we actually are doing a lot of things towards solid and Muller, and we're looking at high power target development, more or less for Muller solid and possibly SBS. And we are unique. We are the world record in high power cryogenic targets. So we're working on more or less development for those targets. We essentially have the magnet from Cornell here, the magnet, Clio 2 magnets on the side. So we're preparing to magnetic static tests and common instrumentations to make it common with the rest. What happens? INC is instrumentation controls. This is a cryo reservoir. Such that essentially the magnet looks and feels the same as other magnets at the laboratory. We are working on general test stands. That is also in combination with the streaming efforts we're doing, part of the EIC detector R&D. That's more to learn more how we read, let's say, CHEM-based detectors out, where we use them in time projection mode past, how we can connect that with planar CHEM chambers, how we can get to streaming. So we're working on that. We're obviously on parity quality beam instrumentation with accelerator. And we're looking at Muller magnets, more or less, different ways how to build the magnet to more or less make it simpler to mechanically build, essentially. So we're still growing, and this is just updated. Just a small week on the call for users in, and we just went over 1,600 this year. So it's not been reported back to my colleagues in the Office of Science yet, but these are the numbers we're going to get. So there's clearly a steady rise of people interested in 12 CB science. Some of this is fluctuation, and this year it looks like most great growth came from the US universities. The other users, other means national labs and industry went a bit down. My guess is next year it goes up again if I look at the trends. It's just sometimes it's back and forth a little bit. From the what? The foreign? Oh, we, as well as the rest of the world, are all unique. Most of our foreign users are Italian. Yeah, so they dominate LHC, they dominate EIC, and they dominate JLab. So, yeah, it's actually interesting. After that, we have a lot of, and so it's almost similar as I would say LHC at CERN. After that, we have a lot of France, UK, Russia, China. Okay, so Italy is the top. Are the Italians smiling again? A huge European contingency. We have less Japan than our colleagues at RIC. We have the hypernuclear committee, but they are more at RIC. Okay, we released a schedule for the next 18 months that includes many high-impact nuclear physics topics. I'm not going to talk much about it. We will complete first phase of FluX. We're doing neutral skin. I'll show you a slide on that later. We continue heavy photon searches. We're looking for a lambda and resonance. There are some estimates from GSI. And because we happen to have this hydrogen-free on site, we happily can see whether that's correct or not. We're looking for the charged particle quark. I'll show you that a little bit more. We're clearly starting the imaging program, transverse polarization of quark inside an unpolarized nucleon. That's part of the LB program. And we're doing a precision study for neutron spin structure. So that's what's on the books for the next 1.5 to 2 years. To give you some example, And again, somebody might show you the same slide too. This is more or less, now we have this LHCb pentaquark, but people are really interested, like, what is this? This is a 5-quark bound state or hadronic molecule. Can you also see it more or less, depending on more or less its production rate in electroproduction? So this is whole B, which is parasitic of the ongoing experiments from group A. What they would get, that's an ongoing experiment. There's a dedicated experiment in hole C, the high luminosity hole. That essentially has to do if the production cross-section is small, they have a better chance of fishing it out. They get then essentially, I think, 5% with a 5% coupling, he has it even in here. This is what you would get in, I think, a week of running. And they sometimes high luminosity, if you know where to look, really helps you. So that's one thing I think will settle pretty soon. Hole D will also get results here. I showed you that earlier. We clearly are going to measure high X structure functions, and this one. This is the D of U ratio, depending on how you do it, with tritium comparing the mirror isotopes, tritium, helium-3, doing parity for latent elastic scattering, where indeed you can separate the D of U. We just talked about that with Darren with this question. You can do that in nuclei also, or with TECT, more as a TECT proton neutron technique. The marathon experiment has been completed. And in the end, if you want to look at large X, you need high beam polarization, high electron current, high target polarization, large acceptance. So marathon, that's this red projection just was completed. To talk about, okay, let's see whether this works. This probably I need to do, well, whatever, I'll have to go. And the neutron skin, there's a little movie here. Probably have to go here.
Click on it.
Probably click on it. You click on it. Yeah, there it goes. Anyway, so that's the happily our colleagues from NASA models are very good always in their visualization. You see the two neutron stars happily merging, and in the end, more meshings of the neutron skin at JLab will contain more what you see at the end, this tidal polarizability of the neutron star has this effect coming in. So we're redoing more or less a meshing, where we're meshing the neutron skin of lead-208. So what's amazing is that you have all these neutrons in nuclei, and we don't really know how much volume they occupy compared to the protons. It just seems so amazing that after so many years we only have model-dependent answers there. And of course, in a neutron star, you also have a crust more or less made all out of neutrons. Anyway, so that's more or less what one of the experiments we are trying to measure, and we're trying to put on the floor in the summer. We are continuing the heavy photon searches. Here are some pictures more or less what people have taken already, this purple. Then essentially Apex will run more early next year, and then you get these kind of exclusion parts. And HPS is unique that I can also look at displaced decay vertices. So you can copulate this area more or less in mass of a heavy photon, brother of the photon, and the coupling more or less. So that's also scheduled for the summer. Well, this is earlier. So that showed you a little bit that more or less in the 12th program there's quite a breadth. I mean, we go from fundamental symmetry, we go to heavy nuclei, astrophysics. I mean, I just showed you some examples of this around the program. Clearly a large part, and I think it's about 14% of the program of proved experiments fit in this area, exploring the 3D nuclear structure. And as you know, more or less, we're happily excited in looking at deep exclusive scattering, to look at electron quark scattering with a Lorentz momentum fraction at a transverse location, or semi-inclusive elastic scattering, where essentially the transverse momentum comes from a convolution of the transverse momentum of a parton and the transverse momentum which is created in the parton to fragmentation process. So we have dubbed that nuclear femtography, which seems like a term which works pretty well. It's good for 12 CV because more or less to look at these beams, you need high luminosity, polarized beams and targets and sophisticated detector system. Well, that's what we have. And at some level, it comes also back to an EIC. That's why we want all the kind of polarization species. We want a large acceptance detector. It comes to the same. So we essentially are doing that. And this is kind of some plots how we can do the imaging again in the valence quark region in the end, be it spatial or momentum, three-dimensional imaging. It's done in all the holes, essentially. In class 12, clearly has the channel survey experiments, large acceptance and medium loss symmetries. They attack both the channelized partner distribution and the transfer momentum distributions. The lion's share of the channelized partner distribution function program is in hole B. If you look at hole C, they will give you more of the precision cross-section you need for long-term transfer studies, you need for ratios. Smell accept how they will get you more on the validation of certain things, be it more or less interpretation to 3D spatial imaging, or more or less the factorization is applicable for TMDs. So that's like this super HMS, the hymometer spectrometer, and the usual auto spectrometer. And then you have an whole A, you have super big bite spectrometer, which can catch to the largest X. Has medium acceptance, high luminosity. That's why you get large X. You need both big acceptance, high luminosity, and the future solids. Just to show you some examples, more or less what my, this is some data sample at 6 GeV. This comes from Hall B, from class. This is what I project for 12 GeV. Now the DVCS scaling check in Hall A has been completed. That's one of the high impact experiments completed. And the deeply vertical scanning on the Heisen, the proton target in Hall B, is ongoing. And to show you a little bit about the 6 GeV world, this is like this pressure distribution from the 6 GeV data, that the constraint you got from the 6 GeV data, that's the yellow, and it's the legend. Sorry, the legend is gone. Then in the end of the 12 GeV would give you the red arrow line. I'm sure you're going to hear about this later. We have started making baby steps to tomography of nuclei on the helium-4 nuclei. First data, I should have put a PRL in there more or less. But I'm sure that Ravel will talk more about that, more or less how we can start. Helium-4 is nice because it's spin 0, so there's only one Compton parent factor. Makes life simpler, so they can start looking at tomography in terms of quarks and gluons. So that's also a piece of the 12 GeV program, which I'm sure will get more and more highlighted at the EIC. One thing is important, like we will likely be the last laboratory who truly does LT separation in the original sense, more or less. You change your kinematics with your spectrometers, reduce your systematics. In the end, you can do also, of course, LT separation by doing beam energy scans. It's likely what we'll do at the Collider EIC. But in the stricter sense, we need some of the data from 12 GeV to make the best out of our EIC data. One of them is more or less the LT separation for the pseudoscalar meson production. In the end, we're going to do LT separations for pions roughly up to Q²10 and for kaons up to Q²6. And based on what we find from 12 GeV will help us more or less what kind of measurements, how much size we can get out of EIC in the future. So that's very important. One of those experiments for the kaons is running now. So that's very good. We're going to get LT separation up to Q²6. But in the end, that's roughly the number. Q² of roughly 10 for pions, up to 6 for the kaons. So that's what we need, I think, for the EIC also. Clearly, we're going to get a lot of momentum tomography. Again, 12 GeV is the famous quark region. There's the more ephemeral super function that transfers momentum distribution from axis 0.45 to 0.45. I'll not tell too much about it. I think most of you will know about it. Jefferson Lab is in the unique situation that we can start a lot of the precision 3D. Combined, of course, with our colleagues. There's data coming in, of course, hopefully from Compass. More in the Z-quark region. Of course, there's also important data coming in from the Hadron Colliders, but we have the electron machine, so we can deal with that. Here's another thing that essentially is important, essentially for the semi-inclusive program. Again, we will be the only one who ever can do LT separation, I think, in this region. So we're going to do LT separation for semi-inclusive and see more where R, the ratio of sigma over sigma t, which we all know for inclusive scattering, what it is actually in semi-inclusive. And it should vary with Z, it should vary with transverse momentum. There's hardly any data to give you an idea. The black is some of the projected insertion we get from 12 GeV. And the color is whatever the world knowledge is at the moment. So clearly we don't know. I always call it, it's a skeleton in our closet. We have no idea. But again, this is something that I think 12 GeV can help the future programs and nail this down. And how do we need, in the end, we need it for our analysis. Pine form factor and structure function. This is relevant. Here you can see the pine form factor. And I told you earlier, you can do LT separations up to about Q²10 for the pion. Well, here you can see the pine form factor. We can probably extract up to Q²8.5. That's because you still need some phase space to get to low T. So you want, it's always a little bit lower than you can do your LT separations. I'll come back to that later because this actually is very much correlated with more or less the acquisition of mass. Pion structure functions. For 12 GeV, we likely can look at more or less what's the behavior of the structure function at large x. Does it go like 1 minus x for the pion or 1 minus x squared? Of course, originally it was this issue, it looks like 1 minus x, and we believe it should like 1 minus x squared. We had this reanalyzed or focus on in company, which shows, yeah, actually, if you reanalyze it, could be 1 minus x squared. Now we want data. So I think that piece, and of course the other one, how you can get there is from Compass. If they do the prion trillion, then you can also get constraints there. Okay, that was my segue to go a little bit about, okay, we're looking at pion and kaon structure at an EIC. So we actually are producing a white paper. We wanted to shoot between 10 and 15 pages. I think we ended with 16, but we're still in the works. We'll have an introduction, have some discussion about mass budget, comparison with HERA and the capacity of the EIC and some measurements. It's based on some workshops we had before. There was also a recent ECT STAR program, just very recent last month on this. And I'll show you some examples of that because I think it's important and to more or less fold it in. I think it has outlook for an EIC. I don't think Sanadine and Cedric will talk about it, so I'll show you what can be done. I think it's actually pretty exciting what you can do. Now, first of all, the pion is always an enigma. Yeah, I mean, at some level, we always show this plot for mass acquisition. And this is true for the quarks, and similar is true for the gluons. So if you start putting your particle fictitiously at rest, it starts acquiring mass. It starts trapping more or less gluons by virtue of the quark-gluon and gluon interactions around it. So we always believe that whatever it is, a quark or a gluon gets addressed mass. That should be universal. Yeah. Okay, there is this happily formula which tells you that pion is a Goldstone boson. That's this formula. Now you can read this very simply that it's saying the pion exists if and only if mass is dynamically generated. Because of B, there's a pion. That's so simple. If the B was 0, there's no pion. Yeah? So at some level, on the other hand, if there would not be a Higgs mechanism, the pion mass is 0. Yeah? So the pion mass is a real. Yeah. To compare that, for the rho, only 6% of its mass squared is given by the Higgs mass. Yeah, so there's clearly a complete difference. Now, this is interesting because we can directly say, what is the impact of all of this for gluon particles using pions versus nucleus? I'll talk a little bit more about that. The next slide will tell you even more. And so, if you would believe in a mass budget, that some of us don't, one would anticipate that at least it's different for the pion. So to talk a little bit more, I'll dig some things up. In the Carr limit, if you use a parton Boydell model basis, the entirety of the proton mass is produced by gluons and due to the trace. This is why some measurements, you're going to hear about it later, want to measure the trace anomaly to constrain this P. And look, whether you believe some of these things or not, well, I believe this actually, but whether you can separate gluons in the trace anomaly from gluons from the anisotropy, you can all argue about. I do think it's probably useful to try to constrain the trace anomaly. On the other hand, in the Carr limit for the pion, okay, I lost the symbol, that's m pi, is 0. There is no trace node. Now, sometimes people interpret that's to saying that in the Carr limit, the gluons disappear and they do not contribute to the pion. You hear that quite a bit around, and that's okay. If that's true, then in a sense you can measure that, whether gluons at large Q squared or not. I don't believe this is true at all. Let me be very upfront. I believe the mass acquisition functions are universal, so there's no way this is true, but you hear it quite a bit. Either way, we can measure empirically, experimentally, that the gluons are in pions and mass fields, yes or no. Okay, so I personally believe that the fact that essentially in the end the pion mass is only given by the Higgs term is because you have a cancellation of terms. But then the EIC can do measurements here. They can measure it. Same thing about the kaon. If you start looking at be it from that, so the Dyson-Schwinger equation, the acquisition of mass, depending whether you have a 0 quark mass or like a up or a down quark or strange quarks, what you'll find is that the strange quark is kind of at the boundary. If you have it, if you have strange anti-quark systems, you have almost that the emergent mass and the Higgs mass general max are similar. So again, you could argue that indeed, if you want to measure the pion again, where does the mass come from? Here's more or less showing you earlier that the gluon also has a mass squared function, so it also acquires mass. So sometimes I always make this plot. This is the emergent, this picture more or less, which our energy physics colleagues say, where Higgs is in the center. We made an alternate version of that, where it's really what comes out here. This is what makes the mass of the universe. Yeah? It's not the Higgs mechanism. It's essentially the gluon and their interaction with up, down, and strange quarks. Yeah? So this is the nuclear physics version of the particle data plot from our energy physics colleagues, which shows you that this is what makes the emergent mass. Higgs can still be in the center, fine with me. Perfect. I'm perfect on time. So, on the proton mass budget, I'm sure you're going to hear more of talks from Cedric and Senedine. Proton mass is almost a GeV. Yeah. You can interpret it as a mass budget or see it as a mass acquisition by dynamical chiral symmetry breaking. Pion mass is small. K mass is somewhere half in the middle. I think in EIC expect contribution to the trace anomaly, and I'm sure you're going to hear more about that from Senedine. And we also can actually, and that's what I'm going to argue in the next few slides, we can learn from it with the sulfur process on the pion decay. I think is really unique for an EIC. And barring measurements with JLab, which won't answer all the questions I'm going to talk about from Compass, it's really unique if we can do it. Yeah. Now, why would it be possible? Well, if you look at the luminosity, what we said to do is about 1,000 times here. In general, the detection fraction in EIC is also much higher than at here because we make a huge effort of integrating our detectors interaction in the interaction region. If you look at the fraction of the pion flux model, the fraction of the proton wave function related to the pion sulfur process, so what's your probability of this to fish this thing out in your wave function? It's roughly 10⁻�3. In here, it's just given for different T-bins. The X, of course, is always here X Bjorken. So that's, of course, this process lives more or less where the pions exist around the C-quark region. So it's about 10⁻³ in a small T-bin. So if you just take these numbers, pion data in ES should be comparable or better than the proton data here, or the 3D nuclear structure data. If you just take the scaling arguments. So if we can convince ourselves, we can map pion and kaon structure for -t smaller than 0.6, so for the k minus 39, we can at least detect it. So all the nice plot models where you show the proton structure function from here up, valuable plot model, you can do for the pion and the kaon. To me, that is very important. Now you can argue, can we convince ourselves that this is true? I think we can. If you look at the earlier 6TV data from JLab, and this is the pion form factor, abstracted as a function of t. You can also, this one went completely wrong. You can also argue more, so you can look at the cross section for a pi plus and pi minus production of deuterium. In the case where you really have a pole dominance, this thing should be unity. It is. So essentially that means that we start getting more and more data that we can constrain the pion, even if it's off shell from data. We will get data where we go to t of about 0.6 from 12 CV. So we will get more of that, but it starts looking that actually in a combination of theory and experimental ancestors, we can constrain the pion structure, the kaon structure, to the physical pion and kaon, even though, of course, what you're measuring is off shell. Yeah? But off shell, now we should not worry about too much. Anytime you do a radiative correction, you're dealing with an off shell particle. So people should sometimes not be holier than the Pope. Here are some examples for pion PDF fit with EIC pseudo data. This is done for this because we happen to have it. We can do we are working on different energies. Don't worry, it's just a lot of work. We more or less have a self-serve pion PDF fit. You can go to the web and essentially you can put your projected statistics in there and you get your PDF out. Done by Nobuo Sato. This is the gray curves is kind of what was on the data based on JLab data and existing HERA data. We don't quite understand why the curve shift. We think it has to do that essentially a lot of the uncertainty comes from the momentum sum rules. But either way, you can see that precision Coulomb constraints of the pion and kaon PDF will be possible. A lot of work still to do, but I think if we can measure below a certain range of t, we can measure pion and kaon PDFs over a long range of x and q squared. Which means that you can see if the Coulombs disappear are supposed to disappear in pion as a function of q squared. You'll see it. Again, I don't believe it. To give you another feeling, the momentum sum rule for the pion structure function tells you about 40% of the momentum is carried by Coulomb at q squared 5. Now, maybe q squared 5 is not high, but it's also not low. So I think there will be Coulombs. We can essentially look at kaon structure function. We can look at large x here. Here are EIC projections, and they're really that good. Yeah? This is essentially assuming again that we can measure below a certain t. Yeah? We make assumptions that we can do it. We have to constrain that. This is important because we believe actually that in the kaon, and this is another weird thing essentially, if you believe that Coulombs in the pion disappear in the chiral limit, we also believe that in the kaon there are less Coulombs than in the pion. because the sensitive strange quark is heavier or radius like students. You can constrain that by measuring the ratio of UK over U pi at large x. This can be done, for instance, at Compass if they get their upgrade, but an EIC, of course, gets you a huge range, and here are the projections. So we get very precise data here, as one example. Here's another example. There's the fine form factor. Now, we can't do the same trick as with 12CV using LT separations, but if we prove that more or less with JLab 12CV that we measure the R more or less ratio, that we can really find the longitudinal cross-section, the polygons of longitudinal cross-section, then you can get pi and form factor constraint by measuring the ratio of the pi minus and pi plus ratio. So again, it's a leap of faith that we will get from 12CV what we think will happen, but then you can measure it to Q squared 35. So I think that would be also a unique measurement at an EIC to get to. And again, the height of this thing, and I don't have time for this, but the height of this thing, how high this form factor in the end will be, how this change will be over, tells you about the mass acquisition by dynamical parasymmetry breaking. Yeah? How fast that mass acquisition goes up. So it's a directly correlated. Okay, my last piece on nuclei. At 12CV, you can measure several things more or less to find more or less how the EMC effect is correlated or not with the effect we found on the dominance of short-range correlated pairs in nuclei. That's this beautiful linear relation. 12CV can look at isospin dependence by looking, for instance, tritium, helium-3, 6, 7 lithium. People are doing these measurements. They can do it initial spin dependence, I'll come back to that. And we can clearly do tech dipole scattering of deuterium because we need it more or less for the neutral structure anyway, to look at U over D. At an EIC, you can essentially do tech dipole scattering of a host of nuclei. You can look, here, look at that, I had it already. You can look at the isospin dependent band, and that will tell you about the difference of the U and the D. Someone really should work this out. You can separate more or less structure and short range correlation. I think someone might talk about that. And you can look at the spin dependence. This is what we can do more or less. This is for 7 lithium. A polarized EMC ratio. So we believe if there's a spin average EMC ratio, there's also be a spin polarized. At 12CV, there's one experimental proof for 7 lithium. We can do measurements more. I don't have the certainty of the measurements in here. But we can more or less see whether this effect is there or not. But I do believe this is also a region where in the EIC you have a huge range of X, huge range of Q squared. You can really map out the polarized EMC effect. And I'm sure Ian will come back to that. Especially if you're in the EIC, there you have deuterium, helium-3, 6, 7 lithium, we have quite some nuclei we can attack. One more thing, if you now also more or less go to more or less stacking and you say you have factor and tensor polarized deuterium, you can find out more or less if quarks are sensitive to the shape of the nucleus by, for instance, measuring the B1 structure function. Like, does it matter? Do the quarks care if, or the gluons care if the deuteron structure is in a dumbbell or a donut? We have no idea. Yeah? So that would be, I think, also a unique measurement in the EIC, which can be worked out. It's not so difficult, it's inclusive. And it directly will tell you whether these things are different. Or we can look at these exotic gluon effects where essentially you have gluon exchange between two different the gluons of 2 different nucleons, which you need to spin one target for and a double spin for. Letters tells us that this is likely non-zero. This would be a unique measurement for an EIC also. So that was the last part that I think 12CV science at JLab is underway. We are in 4 whole operations. We have a broad program approved, 10 have been completed. The schedule has been released through calendar year 90. We're actually working on the schedule, releasing it through calendar year 20. That's partly because some maintenance tasks drive the schedule anyway, so it's not so difficult. Many high impact experiments. We have initial science results. We're working on future equipment. We believe that the 12CV output to EIC is rather transparent. There's an LT separation program at JLab, which is a must for EIC, pion, kaon, 3D structure. We need some of these LT separations. We need some of the legwork of 12CV. It clearly is in a good position to spearhead the nuclear femtography program. And for us, JLab construction operation is concurrent with 12CV, so I won't bore you with timelines and just like that. It's kind of transparent. I think the future EIC is taking shape. There's much activity, which is great. International activity too. And I folded in two pieces which I think we should fold in the new EIC white paper. One is the structure of pions and kaons and the origin of mass, how that's related. Beautiful area for an EIC. And one is the use of polarized light to medium heavy ions and tagging formulas, looking at isospin dependent up and down quark, looking at exotic gluons, looking at whether you can find quark difference from the dumbbell and dominant. Looking at the helium-3 wave functions, that's what Richard will argue about. There's a lot of outstanding issues there. Thank you.
Questions? Sorry.
Just a question. So you mentioned that Carl would
All right, man, you can ask the theorists for that. I mean, as far as I know, this is what
I see no reason why she is zero. It's coming from. I mean, KWU is proportional to the.
It's because
it's for the pion.
It's for the pion only, isn't it? The
At
pion,
the same time, the nucleon one is not zero, while the pion one is zero.
it's only for the pion because the mass is zero.
Oh, okay. Just okay.
Here it's not, isn't it? This is for the proton.
Right.
And here it's non-zero. So in the end, actually, this is why a lot of people are interested in the proton, because they believe in the chiral limit. It's all due to the trace anomaly. So that's why you sometimes will hear, to understand the proton mass, we have to measure the trace anomaly. I'm saying just that's what you will sometimes hear. I don't agree with it, but that's what you will sometimes say. Yeah.
But,
In here, essentially, it's zero because the pion mass is zero.
no, if I may comment, I don't think we need to have a problem with this in the following sense. If you look at GeV's decomposition, it's a choice where if you take the chiral limit, you can actually decompose the mass in terms of contributions of the constituents. Let's say you took the first frame and you have quark contribution, kinetic and potential energy, and kinetic and potential energy of gluons. And you can even set, if you do it on the pion, you could set the piece that he has 1/4 of the trace anomaly to zero, but doesn't
No, you
mean
cannot.
that the constituents.
The pion, you can't even define the frame.
No. What
You
I'm
cannot. Pion, you can't even define that rest frame.
No. But
So
what
this
I'm
is
trying
not
to-
true. It's just not true.
I
You cannot do that.
All right, so it's not equal zero, it's in the limit. I still define a frame, right? You agree that if it's
I'm
not
sure you're going to hear
equal-
more about it from Cedric. It's to me very arbitrary whether you find gluons coming from the trace anomaly or from the gluon energies. I think it's completely arbitrary.
what
It's
I-
A, frame dependent, what she is doing, and B, it's essentially interpretation dependent. It's nice, but and that we want to measure the trace anomaly, I'm fully supportive.
Can I finish my comments? The only thing I'm saying is that there is value in trying to get the piece of the mass, let's say, of the pion from its constituents. And the constituents of the pion are quarks and gluons. Okay, they're not just quarks. And I'm just saying that while the trace anomaly for the pion gives exactly zero for cancellations in the chiral limit, let's say it gives zero, that everybody kind of agree on. The only thing is that doesn't tell me that there are no gluons in the pion. That's the only thing I'm trying to say. What I'm saying in that case is that the pion has a mass. A good part of it is coming from the quarks, but in some decomposition, you can express what is the contribution of the gluons to the pion mass. That's
So you're trying to suggest there might be gluons that do not contribute to the trace anomaly.
trace
That's what
anomaly
you're trying to suggest.
It's
Yeah.
subtle.
Just because they're pions doesn't mean that they contribute.
When you write the scaling variance decomposition, it's two terms. You have no choice. You do the trace anomaly zero, then you are left with the quark mass. But if the spirit is to go and let's say choose a frame and some decomposition, and I'm not taking the quark masses to zero. Okay, I don't want to do the chiral limit. I have a piece that's a trace anomaly and a piece that's quark contribution. If I choose a frame and do a certain decomposition like G did for the nucleon, and he had a reason why he did that, because he said, oh, I can get, for example, the part that's the contribution of gluons from deep inelastic scattering because it's linked to the energy momentum tensor. So in the pion, you could choose And I agree with you, it's not unique, right? Trace anomaly will give you 0, whether you like it or not. And the point is that if you go to that friend, you can talk about gluons in the pions. You can't throw them away. There's no way you throw them away.
The discrepancy is that you are arguing whether you can or cannot go to that. That's
For the pion, you can't go to that phrase.
This is what.
No, but the other thing is true. That it is true that, and I can tell you, these are venerable scientists, which I've heard make this statement. In the chiral the gluons disappear and thus contribute nothing to the pion. That's factually incorrect. I'm sorry. I agree. I'm just telling you, these are not the least theoreticians.
I'm not defending that argument, by the way. I'm just trying to say that in ion,
I think we should just measure the pion, the chaos structure, and I also think we should measure the tracing.
I agree with that.
We need to make progress. I agree with that. I was just trying to put some people go too far in their arguments. That's what I'm trying to point to. And there are unique things an EIC can do unambiguously.
Yes, so we agree that I could measure gluons in the pion, right? In principle.
I think so.
That's right. So that we don't disagree on.
Well, you have the agreement, so Andrea.
I was wishing to ask about the polarized target of the JLab measurements. Are all there, or if there are some of them that has to be counted? Or
Depends what you mean, isn't it? We clearly are ramping up for I would call it a super duper polarized helium-3 target. Which essentially can stand unlimited luminosity almost. We clearly can have a regular dynamically nuclear polarized solid state target. I think we should build another magnet for those because we had some issues with the one before, and we can also emphasize it more for transverse pin physics. My guess is your question comes to whether we have essentially polarized HDI targets for a piece of the program. That piece, I think, is still outstanding. We are trying to do an electron test by the end of this fiscal year.
Okay, and also, if I can comment.
If that was your question, was.
That was my question. Yes.
Yeah. I think depending on what we find there, we anyway have a backup road going into where we want to look at what's another way to make a transverse polarized DNP solid state target with a larger acceptance. So we work on that anyway.
And also, if I can comment about the complementarity, I think that for what concern the PDFs of the ion and the kaon have been measurements done pion and pion pins and with offset mesons and compare them would be very important.
Yes.
See if the approach that we are taking is safe enough.
No, in reality, the pion, like a K vectorial A, will more or less give you more or less the additional measurements, the complementary measurements. B, it will make this much easier for EIC measurements to know what your pion or kaon flux is. Because now you know where you overlap. So yes.
Okay.
Yeah, I had actually a question of something you didn't address in your talk. Do you think you will make progress in understanding the standard form factor and resolve the discrepancy which we still have between the double polarization and the recoil method? Because from our understanding right now, the two photon exchange doesn't really fully kind of explain this. So I'm wondering, is there a plan for 12 JeV how to address it?
No, essentially we, well, yes and no. We essentially, I skipped the form factor slide. It's clear that the form factor will get Q squared to 1020 for all the form factors. The two photon exchange, no, essentially you're correct, isn't it? Even if you, after 3 different experimental efforts, it's still, it's somewhat, there's not a real conclusive answer. Everybody more or less sees some hints of the two photon exchange, the box diagram, but there's no conclusive answer to explain it. People are talking in whether you could make a positron beam at GeV, but that's of course costly.
I know.
So no, there's no direct answer for you. There's not much we can do. We can do imaginary parts by looking at a normal polarized nucleon and see what you get. But that doesn't give you the real answer, in my view. That's an imaginary part of the two photon
Why I'm
exchange.
asking is we are
No, it's a problem still.
talking about the properties of a proton
Yeah.
spin charge is one of them as well. And so
Yeah.
If we don't have a full understanding of it. Okay.
Well, I mean, my view, and okay, you didn't hear that from me, but it's the same with the proton radius, isn't it? Yeah, now you're going to see some preliminary results for PRAP, that's great. In the end, I think we have to live with it. 5 years from now, we're still going to be arguing about the proton radius. That's my perspective.
Let us thank Rolf and other speakers.